think we can go ahead and get started. So it's a great pleasure to welcome Professor Ricardo Betti from the University of Rochester to give today's colloquium to us. So just a little bit of background on Ricardo. So he's, to get the names right, I have to read here. The Fred H. Gowan Professor of Mechanical Engineering, but he also has a joint appointment in physics and astronomy, so he's also Professor of Physics and Astronomy at Rochester. He's also an assistant director for the Laboratory of Laser Energetics, which is operated by the University of Rochester. I think he's going to be focusing primarily today on results from the National Ignition Facility at Lawrence Livermore, but the LLE, the Laboratory for Laser Energetics at Rochester, is home to another very powerful laser known as the Omega facility. So that's a 60 laser system that I think has a total energy of 40 kilojoules and does similar physics. He may show results from both, I'm not sure. Besides his interests in inertial confinement fusion, which we're going to hear about today, he also has a large hand in the magnetic confinement side. So he's made major contributions in topics like MHD for that. So we see him a lot in both sides of the community. He's won a number of awards. He's won the DOE Ernesto Lawrence Award. He's won the Edward Teller Award from the American Nuclear Society. He's also won the Excellence in Plasma Physics Award from APS. Of course, he's very involved in a variety of community exercises and program planning and the like. Maybe notably, think just coming off as serving as vice chair of Fusion Energy Sciences Advisory Committee. Are you off? Yeah, I think you're off. So with that, let's welcome Ricardo here.
Thank you, John. So this is a physics colloquium, so I prepared a talk that everybody can understand because everybody here is a fusion physics expert, right? On the other hand, is not really extremely low level, because you're all physicists, okay? So I hope at the end of this talk you understand what's going on at the National Ignition Facility. You probably heard in the press, the popular press, results from the NIF. When it comes to fusion, there is a lot of misinformation, on how close we are to fusion power. Well, let me just say, just for the record, we are very far from fusion power, okay? So there are no doubts about that. And so we're going to talk about it today. So a little bit first of zeroth order concepts for fusion, and then a little bit into the physics of what's going on in NIF. Okay? So I work with the NIF people. So I'm not a Livermore employee. I'm a Rochester employee. But I work with them, so I know what goes on, and I review them in different committees, so I know, pretty well what is going on and how to interpret the results. So for those of you that don't know about fusion at all, okay, so fusion is basically based on a reaction between two hydrogen isotopes, deuterium and tritium. That's the fusion that we know today, or that we are pursuing today. And these fusion reactions make a neutron energetic at about 14 MeV. And of course, the neutrons goes away because nothing stops it. But then this reaction makes an alpha particle, which has 3.5 MeV. And the most important ingredient of all of this right now, that's what my talk is going to be about, is that this alpha particle here, since it's a charged particle, will slow down in a plasma, if there is a plasma around it. And in particular, we slow down on the electrons by collisions, and we release the energy to the electrons. The electrons gain the energy of the alphas, and then by collision, they transfer the energy to the ions, and therefore they keep the ions hot. Now you can imagine that if you have a lot of fusion reactions, and therefore you have a lot of alpha particles, then the electrons become hot. This heat goes from the electron to the ions become hotter. And as the ions become hotter, they make even more fusion reactions. And so you can understand that this can be a runaway effect that causes this plasma is to ignite, it's called. Basically, you can think of an explosion, okay? So, so the ignition condition for which this, under which this plasma ignites is that the power that is released by the alpha particles to the plasma exceeds the power that is lost by the plasma. The plasma can lose power in many different ways. In magnetic confinement, it does lose power in many different ways. In inertial confinement, there are fewer channels, but still can lose power. Okay, so some people call this phenomenon, this runaway phenomenon, the thermonuclear instability. We call it ignition, basically, when basically this heating of the plasma by alpha particles goes out of control and runs away. So in terms of some jargon here that is used in the fusion community. So imagine that you have a fusion plasma. The fusion plasma makes fusion energy in the form of neutrons. This laser is not a Rochester laser, that's for sure. Okay. This is a very faint, maybe Livermore laser like this. Okay, so the fusion power here comes out in the forms of neutrons, again, and alpha particles. This slows down into the plasma, it self-heat the plasma, the alphas. There is also energy provided to the plasma that just to get the plasma hot enough to make enough fusion reactions. Okay, here we go. It's a Wisconsin laser. Much better. Okay. Okay, so there is input to the plasma. This is external input. There is self-heat from the plasma, from the alphas, and there is fusion energy output. So people that do the work on fusion, they define the parameter. I call the thermonuclear Q, or I call it the physics Q, which is just the ratio of how much fusion power you get out divided by the input power to the plasma. Okay? I think a better physics parameter is not this Q, but is Q sub alpha. So Q sub alpha, instead of having in the numerator the fusion energy output, has only the alpha energy of that. So it's E alpha. Okay? So this would be the alpha energy that stays into the plasma as compared to the input energy. That's Q alpha. Because the ratio of the alpha energy to the neutron energy, this is 17 MeV, this is 14 MeV, and this is 3.5 MeV. So that ratio is just 5. So the ratio between the thermonuclear Q and the Q alpha is just 5. Why this Q alpha? I like this Q alpha because that tells me that how much alpha heating there is from the alpha, that's the self-heating mechanism, with respect to the input heating external from whatever input heating you are thinking of. In magnetic confinement, the input heating will be radio frequency heating, neutral beam heating, ohmic heating. In ICF, instead, the heating comes from compression due to a piston, because that's what the laser does, drives the piston to compress the plasma. Okay? You can also, some people, if you look at, there's a famous, famous, I'm not quite sure, but it's a FISAC report. It used to be on FISAC a long time ago. And the definition of this figure of merit was the so-called fractional alpha energy, or alpha heating. So basically, it's the fraction of the heating to the plasma that comes from the alpha, the self-heating, with respect to the total heating, both external input plus the alphas. So basically, you can tell that a plasma would be alpha dominated, so the alpha heating would be dominating over the external input, if this ratio is larger than unity. So Q alpha equal 1 would be the threshold. That corresponds to a thermonuclear Q of 5, or an F alpha of 1/2. So when you exceed this threshold, then the alpha heating exceeds the external heating, and we have a dominant alpha heating or a burning plasma, where F alpha basically is larger than 1/2. So more heating comes from the alphas than the external heating. That's very simple. So people in ICF also talk about target. ICF stands for inertial confinement fusion. They talk about target gain. So target gain is a different beast. So the target gain, if you think of a target chamber here, and the laser hitting a target, so then you can think of producing an energy balance across a control volume that includes the target chamber. So you would have laser energy going in, nuclear energy coming out. So then the target gain would be the ratio of the nuclear energy output, okay? But now in the denominator, you don't have just the energy going into the plasma that makes fusion reactions. So you would have all the laser energy that go into the target chamber. Now in inertial fusion, most of the energy from the laser doesn't actually end up in the thermonuclear fuel, which is deuterium and tritium. It goes, I'll show you in a minute, it goes to a lot of different places, okay? So anyway, if you think of fusion as an energy source, you are concerned about having a system for which you supply energy to get it going, but then you get energy back that is more than the energy that you supply to it. So then it makes sense to define a gain as the fusion energy output divided actually the driver energy, in particular laser energy in this case because the driver is a laser, going into the target chamber. So that's called the target gain. And for example, the driver energy for a NIF laser would be 1.9 megajoules because that's what NIF puts out in the UV. So that what goes into the target chamber, 1.9 megajoules, okay? Now, if you're thinking about electricity, and I'm going to stop very quickly talking about fusion energy because, as I said, it's still light years away, so why bother? But if you think about really fusion energy, then you really need to be concerned about a different parameter, which is so-called the engineering Q, which is the electrical energy output divided by the electrical energy input, right? So you want that parameter to be larger than 1, so you make actually useful electricity. So if Q is equal to 1, it means is electrical power break-even. This is just a sketch of how a hypothetical fusion energy plant would work based on IFE. You would have a target chamber, you would have laser beams, you would have a target factory, and then target injected into the target chamber, and then you repeat this implosion process many times a second, and that will make enough continuous power that you can produce useful electricity and put it on the grid. So the break-even electrical would have a QE equal 1. If you have QE equal 5, it means 20% of the energy that you produced is used to drive your plant, so that's the recirculating power. If you have QE equal 10, only 10% is recirculating and 90% is used goes into the grid. So if you're thinking about energy, if you want to start comparing magnetic confinement with inertial confinement, you really ought to look at Q sub E. And for both of them, Q sub B is so small, okay, that we don't want to really go into the detail which one is the smallest, if it is 10 to the minus 10 or 10 to the minus 11, okay? Okay, so high target gains are required for IFE. So if you think about IFE, inertial fusion energy, okay, and then you have, you say, well, I want to build a plant that has 10% of recirculating power. So my engineering Q is 10. And the drivers, well, at the most you can get maybe 10% and maybe 20% out of a laser driver. So this is a driver efficiency, or wall plug efficiency. So you need to power your laser. You need to take energy, electricity to power your laser. And the laser puts out 10% of that electricity into light. And if you have a thermal cycle that is 40%, you just do the math. To power this plant, every target, okay, this uses a 10 hertz laser. Every target must produce about a gain of 230, okay? So that means that you put so much laser energy in, every explosion of that target has to give you 230 times the laser energy that goes in. If you can live with 20% recirculating power, same parameters, just now QE will be 5, then your gain will be half of that. So you can live with 115 gain. If you can make your driver efficiency 20% instead of 10%, then you can live with a gain of 58, roughly half of that. Okay? Now, where do we stand now? So look at the NIF laser. So the efficiency of the laser is extremely small. So the NIF laser has an efficiency of 0.0066. Okay? So that means that if it takes 1 megajoules of electricity from the capacitors, it makes 0.0066 megajoules of light. Okay? And even if you can get a target to light and so to ignite and get a gain of 1520, your engineering Q will be only 0.05. Okay? So it's a very small number. Okay? However, NIF is a single-shot facility. It's not meant to be a facility for energy applications. So it's not designed for that. It's a glass laser. It's a flash lamped. Flashlight pumped laser. Flashlight pumps laser. Instead of a diode pumped laser, that's what you would use if you want to make a power plant, a diode pumped laser, which is much higher efficiency than the NIF laser. So, talking about relevant energy applications of the NIF, it's not productive. NIF is really a physics machine, a single-shot facility, and that's what design is. Really funded for national security. That they couldn't care less, the people in national security, about making electricity for the grid. Okay, so that makes sense. So just to give you the best results to date on NIF. So if you want to estimate the thermonuclear Q, so the ratio of the fusion energy output to the energy that ended up in the thermonuclear fuel only. So then the ratio is 2.4. So the thermonuclear fuel received X and produced 2.5 times that X in fusion energy. So that's actually an interesting result from the physics point of view. However, if you look at the actual gain, which is fusion energy over laser energy, that is 1.4%. Okay? So for this to be an energy-making process, we are still so far away. This is only 1.4%. And if you calculate the QE, electrical output to input, I just put 0 plus because it's so small, this number, that I'm not even going to bother. Okay? So inertial confinement is just physics right now. So, and like magnetic confinement. Okay? They are both in the physics stage. So really talking about how many megajoules you have produced, I have more megajoules than you, and it's 0. Okay? All right, so. Okay, so no more talking about energy. So only physics from now on. Okay, so we put the energy to rest. So let's talk about implosions. So inertial confinement targets are imploded by the rocket effects. You shine on the target a laser directly, or you can use X-rays produced by a laser to ablate the surface. The material that is ablated off for conservation of momentum will give you a push inward, and that's how you implode the target. So you can have a direct laser irradiation, shining the laser beam directly on the target. You can shine the laser inside a cavity, which is called, it's a metal cavity called the hole round. The gold, it's made of gold. The gold gets hot. It produces black body radiation. And the X-rays, it's a thermal bath of X-rays. It's the X-rays that drive the ablation on the surface of the capsule, and that causes the implosion of the capsule. So we're going to be concentrating mostly on indirect drive because that's what is pursued on NIF right now. So this is the actual size of the whole realm. It's a centimeter scale object here. The NIF laser beams, they penetrate the whole realm from the top, from the North Pole and from the South Pole. They enter, they go on the wall, they are absorbed, X-rays is produced, The thermal bath of X-rays implode the capsule. The capsule, this is a picture of the actual hole round. Okay, you can see here. And the capsule is very simple. It's about a 2 millimeter size capsule. It's not that simple, but it's a 2 millimeter diameter shell. It's got an ablator. So this is a shell of, right now is plastic, and is doped with silicon. This is to change the opacity of the plastic to stop the X-rays. And then inside there is a thin layer of deuterium and tritium ice. So this is solid. So it's roughly at the triple point. So it's 18 Kelvin. And it's in equilibrium with some vapor. Okay, we call it a gas. Okay, and this is the vapor that then gets compressed and makes a hot central spot in the middle. Okay. So this is the kind of capsule that is imploded on NIF these days. You can change the ablator and you would have a different capsule. So one very important thing to remember is that these implosions are hydrodynamically unstable. So if you have a surface perturbation of the capsule, the surface perturbation grows exponentially fast during the implosion and makes all kinds of distortion present on the surface of the capsule, okay, when the laser is accelerating the capsule. And this because you have two materials. You have the ablated plasma around it that is low density. You have the shell, which is high density. And the capsule is accelerated by the laser or by the X-rays. And therefore, it's an accelerated system. If you are in the frame of reference of the capsule, you will see an inertial force going from the inside to the outside. Therefore, you have like a heavy fluid in equilibrium with a light fluid in a gravitational field, and that's Rayleigh-Taylor unstable. So you would have the Rayleigh-Taylor instability developing. So the Rayleigh-Taylor instability grows, and then the target, as it converges, starts building pressure in the middle. As the pressure builds up, it will slow down the imploding capsule. And now you would have the inner surface decelerating, so that we have the acceleration on the inner surface that becomes unstable again to the Rayleigh-Taylor instability. So you have a Rayleigh-Taylor instability on the outside during the acceleration phase, on the inside during the deceleration, the slowing down phase. When the pressure builds up in the center, it slows down the capsule. Okay, so driving ICF targets is a very, very inefficient process. So only a small fraction of the driver energy is actually converted into useful kinetic energy. Okay, so in indirect drive, the laser has to go on the wall or the hole round, heating up the gold. So a lot of the energy is lost into making the gold hot. Okay, so of the X-ray energy produced in the black body radiation, only a fraction of that ends up on the capsule. And the fraction that ends up on the capsule, most of it goes into making this plasma, or ablated plasma, hot. Okay, it's like a rocket. So all this plasma gets heated up by the X-rays. Okay, ultimately, what we care about is driving this piston, which is the shell. So ultimately, what we care about is only the kinetic energy of the thermonuclear fuel, the DT. And so most of the energy goes into heating up the gold to make X-rays. Most of the X-rays energy actually doesn't even go on the capsule. And whatever goes on the capsule goes into heating up the plastic, which is the ablator. So only a small fraction at the end of this process ends up in the DT, which is the thermonuclear fuel. Okay, so the kinetic energy that you get at the end, which is the amount of mass left after it has been ablated, half times the velocity square, that's the energy that you care about that you can use to make fusion. That's all you have. Okay, and this is a very small amount. So for a NIF capsule, the laser energy, let's say 1.8 megajoule, the final kinetic energy of this is only 10 kilojoules. So then you have only 10 kilojoules to work on to ignite the plasma. That's all you got. Okay? And the total efficiency of this process, you just take the ratio of these two numbers, is just 0.6%. Okay? So from the plasma physics point of view, okay, well, there is plasma physics going on in the whole round, but for the fusion plasma physics, you are only working with a 10 kilojoule plasma here. Okay? Okay, so not only that, but now you have, let's say, an imploding shell made made of deuterium and tritium. And this kinetic energy of an imploding shell, it gets distributed roughly half and half. So as the exploding shell stagnates, okay, you end up with a configuration like this. So at peak compression, you will have a hot, low-density plasma in the middle, usually a temperature of several kiloelectron volts. And here I'm plotting the results of the simulation. This is radius. Your internal plug, this is temperature. You can see the temperature is several kiloelectron volts inside the central region. And the central region is only slightly like 20, 25 microns in radius. So this is a very, very tiny, small spot. It's hot, several kiloelectron volts. But the density, which is in blue, okay, is relatively low. Relatively low because it's really high, but relative, the central part to the surrounding part is low. So this, we are talking about hundreds of grams per cubic centimeter. The surrounding part instead is as 1,000 grams per cubic centimeter. So you have now a dense shell surrounding a hot plasma. This dense shell is also made of deuterium and tritium. It's just very cold. The temperature here is low, so there are no fusion reactions occurring here. Only the fusion reactions are taking place in this central part. Okay? And so half of the kinetic energy that the deuterium and tritium fuel gets, half of it goes into building this hot spot, making it hot. And the other half roughly goes into compressing this dense shell around it. Okay? Now, when you take magnetic confinement, okay, so magnetic confinement, you build the confinement system is the magnetic field. Well, here the confinement system is the inertia of this shell. Okay? So that's what confines this hot plasma. So this 50% energy of this kinetic energy, already only 10 kilojoules of this, 5 kilojoules goes into building this confinement system, so like your magnetic field. Okay? And the other 5 kilojoules goes into heating up the plasma to make fusion reactions. Okay? So that would be your RF heating, okay, or ICRH, or neutral beam. And this would be your magnetic field. Okay? So at the end, the plasma that makes fusion reactions has only 5 kilojoules of energy. Okay? So now, so the input energy to the hot spot, that's the hot plasma, okay, it's only kilojoules level, several kilojoules. If you ignite these plasmas, then you can amplify that energy by a great amount. Okay, so for instance, so let me give you an example. So let's say that only 5 kilojoules goes here and 5 kilojoules goes into making the dense shell, which is the confinement system. Let's say that this plasma ignites and makes 1 megajoules of fusion energy. Okay, that is equivalent to an amplification. There is 5 kilojoules here. It makes 1 megajoules, an amplification of 200. Okay. What about the self-heating level? Well, the alpha particles are 1/5 of the fusion energy, right? So it would be 200 joules. So 200 joules of the heating come from the alpha particles. So the input heating was only 5 kilojoules. So you have alpha particles providing 40 times more energy to the plasma than the input energy, okay? So that's really, you know, a very burning plasma. So that's an ignited plasma would be, okay? Where the alpha particles are 40 times more energy provide that the piston does, okay, to the hot spot. Okay, so there is also another stage that if you have a robust ignition takes place. So ignition is thought as an amplification of the fusion energy in the hot spot itself. But remember that all the surrounding fuel here, well, all surrounding mass is actually deuterium and tritium, so it's thermonuclear fuel. So if you can ignite this central hotspot strongly enough, so robust ignition, then because the alpha particles producing the fusion reactions, okay, there are going to be a lot of them, they will try to leave the hotspot. As it becomes hotter and hotter, the range of the alpha particle becomes longer and longer. So the alpha particles start penetrating into the dense fuel, put deposited energy into the dense fuel, and advance a fusion burn wave through the dense fuel. So in that case, you would have a propagating burn, and then the whole plasma, including this dense shell, will start burning. So in that case, then you would have an enormous amount of fusion reactions. So if you have, in that case, let's say a 10 megajoule fusion yield, then you start with a 5 kilojoules hotspot, and that would be amplified a factor of 2,000. And the alpha heating would be a factor of 400 times more than the input energy. So that would be the case of a propagating burn, and that's what you really need to get if you want to show that you have an energy source, so you have a high gain implosion. Okay, so how can we derive stuff in a simple way? So I can derive pretty much everything using a very simple energy balance equation for a fusion plasma. And I can do this in general, and this is not strictly applicable to, for instance, magnetically confined plasma, because magnetically confined plasma, you keep inputting energy into the plasma at all times, and it's steady state, more steady state at least, than inertially confined plasma. So, but with small changes, you can apply this to magnetically confined plasma, and then you can compare the magnetically confined plasma to the inertially confined plasma. Okay, so for now, I'm going to apply this to inertially confined plasma. So I'm going to take a plasma here, this one, that has been compressed. So it has been heated up by a spherical piston, which is my imploding capsule, my imploding shell. So imagine that this plasma is being compressed at a given pressure. I call this given pressure P no alpha, because I'm imagining that this pressure has been reached without contribution from the alpha particles produced in the fusion reaction, simply by the piston action of the imploding shell. So I have this piston, compresses the plasma to this pressure P, and I call P no alpha. The alpha particles are not on yet. No fusion reactions have occurred. Imagine that. Okay? And I call this time T equals 0. From that time on, I'm imagining my fusion reactions start taking place, and I'm going to increase the energy of this plasma. Okay? So I know that this plasma also loses energy, like all plasmas do, and I call tau the confinement time, so the time over which this plasma loses energy, the time scale. So then I just write now an energy balance. Okay, the time or rate of change of the energy of this plasma, which is 3/2 times the pressure times the volume, that's the energy. Okay, there is an input energy coming from the alpha particles, and this is the alpha particle, this is the fusion rate, this is the fusion reactivity, sigma b, which is a function of temperature only, times the density of the species. It's a 50-50 deuterium and tritium, so it's just one density species, and square, times the energy of each alpha particle, 3.5 MeV, times the volume of the plasma itself. So that's the energy source coming from the fusion reactions, from the alpha particles. And then the energy is lost over a confinement time tau, so I just put a negative term, which is a sink, 3/2 PV over tau. And I'm going to solve this equation starting at the time 0, which I define as the time when my plasma has reached this pressure, which I call P no alpha, without any alpha contribution, as I said. Well, that's a simple equation to solve. Okay, first I rewrite this equation like this, okay, where this S alpha is a function of sigma b, which is the fusion reactivity, and the temperature T squared. So this is just a function of temperature. And to make life simple for myself, it is actually an approximation that works better for magnetically confined plasma, which the temperature is higher than inertially confined plasma. I'm going to take sigma v that is proportional to T squared, which is true if the temperature is sufficiently high, over 7 keV, then the reactivity goes like T squared. Below 7 keV, it goes like T cubed, and eventually a low temperature goes like T to the 4th. But anyway, just for simplicity, let me take sigma v proportional to the temperature squared. That's the reactivity. So then T squared here and T squared there cancel. And so my S is just a constant. That's the simplest case. Okay? And now I can write everything in dimensionless form. For my pressure, I write it in its dimensionless form using the initial pressure that I achieved without any contribution from alpha particles. And then the time, I used the confinement time to make it dimensionless. And of course, the initial condition would therefore be that P hat would be 1 at time 0. My equation becomes trivial. Okay, it's an ODE. And this parameter chi is nothing else that the initial pressure times the confinement time divided by this constant here, S alpha. Obviously, S alpha is the dimensions of P times tau. Okay. So I call this the no alpha Lawson parameter. I mean, Lawson worked this out not exactly in this form, but in similar forms in 1956. Okay. Okay, so I can solve this dimensionless equation. There's really nothing to do here. It's a trivial solution. And I get this solution. okay, in terms of this parameter, chi no alpha, okay? Now, this solution, you can see, has an explosive instability going. If chi no alpha is larger than unity, then this term becomes, this is positive, so eventually, for a given time, the denominator goes away and you get infinity. So basically, if you plot p hat, okay, for chi no alpha larger than unity, I pick 1.5, you will get an explosive instability. So that's an ignited plasma, okay? That's an ignited plasma. If chi no alpha is less than unity, then this terms becomes negative, so this is positive, and so p hat will just decay in time. Okay? So for chi no alpha larger than unity, you have an explosive instability, and that's ignition. Okay? If for chi no alpha below unity, it will not ignite. The plasma will just, the energy of the plasma will eventually decay. Okay? So the key parameter is this chi no alpha. Okay, that determines whether the plasma ignites or it doesn't ignite. Okay, and this chi no alpha, as I showed you before, is just a ratio of the initial pressure, the confinement time of the energy, divided by this constant. But this constant, by definition, therefore, remember chi equal 1 is the marginal ignition condition, would just be the lowest value of p times tau that produces ignition. That's by definition, therefore. So sometimes people call it this S alpha, they call it the P no alpha tau minimum value required for ignition. So when this ratio is 1, you get marginal ignition. Okay. Okay. So I can now define two things. So this is it's not obvious now why I'm doing this, but it will be in a minute. So I know that we don't have an ignited plasma on NIF. Okay, so, but we have a plasma that has a significant amount in the last experiments of fusion reactions. So it's a plasma where we think alpha particles are significantly heating up the plasma, okay, are actually the major contributor to the heating of the plasma, okay? And people that work in the fusion sciences, they are very excited about that, when alpha particles are actually doing something to the plasma to make it hotter, okay? And they do this in a significant way. Now, the problem is, how can I quantify what is the alpha particle heating with respect to the external heating in the plasma in NIF? Okay? So I'm going to do the following. First, I'm going to define a neutron yield. So neutron yield is the number of fusion reactions, because I can measure neutrons, so I know how many fusion reactions are produced. Okay? So this is the neutron yield, okay? And I call the neutron yield with alphas. Of course, in an experiment with deuterium and tritium, I'm going to have alpha particles. There's no way to get around it. And so the alpha particles will affect the energy of the plasma and will affect the number of fusion reactions by the self-heating mechanism. However, if I have very few fusion reactions, then the effect of alpha particles heating is very small. Okay? So whether I switch them on and off, ideally, it wouldn't make many difference. But in an NIF plasma, we think that the alpha particles are doing a lot. So in an experiment, the alpha particles are there, okay? So the neutron yield that I measure is affected by the alpha particles, and I call it yield alpha. This is the one that actually I measure. So the neutron yield is basically sigma v, which is the fusion reactivity, times n squared, which is the density, and so that would be p squared, and t is p divided by 2, okay? So I'm going to rewrite p squared at p hat squared divided and multiplied by the initial pressure. So there is no initial pressure in the product of these two, right? Because I'm just dividing and multiplying. And this is, I write the p hat that I just calculated. And this is times the volume of the plasma region, times the time over which the fusion reaction takes place, which is the confinement time. So I can do now this integral, and I calculated p hat before, and so I get this expression in terms of this Lawson parameter, which is just p tau divided by the minimum value of p tau required for ignition. And I know the chi now, I'm in a sub-ignited plasma, so chi is less than unity, so everything is finite here. Okay, so this is the neutron yield that I measure, depends on these parameters, the chi, the volume, the confinement time, and the pressure at which I brought that plasma initially, before the fusion reactions modify it. Okay? Now, if I could, okay, in an ideal world, of course I can do this in the codes, okay, I could think, well, if I want to measure what is the effect of alpha particles to the plasma, it would be nice if I can do an experiment where magically I turn off the alpha particles, okay, just they are not there, and then I compare the experiment with alpha particles with the experiment without alpha particles. So that would tell me how important the alpha particles are to the heating of the plasma. So, of course, I cannot do this in the experiment. I cannot turn off the alpha particles in an experiment, okay? But in theory, I can. So I go back to my energy equation, and this was the source term coming from the alpha particles. I just get rid of it, okay? And now I just solve the PdT equal minus P, and then my pressure, of course, decays, okay, in time. So that would be my pressure without alpha particles, okay? And then I substitute back into the yield to say, well, what would have been the neutron yield if the alphas were not on, okay, were absent? Well, then I just calculate the same formula as before, but now I use the P hat equal to this. I substitute there, and then I got my neutron yield without alphas, okay? So that's only an imaginary neutron yield. In the experiments, we cannot turn off the alpha particles. Okay, but obviously a measure of the effect of alpha particle heating would be the number of fusion reactions, the yield with alphas divided by the yield without alphas. That would tell me what kind of yield amplifications is caused by the alpha particle heating of the plasma. Okay, so in theory I can calculate that. I take the ratio, and the ratio depends only on that Lawson parameter, P times tau, okay, divided by a constant. Okay, so I can plot it like this, okay. And well, I can say that, well, if I know what is chi, this chi here, then I can estimate what is the yield amplification due to the alpha particles, right? What is the problem? The problem is that, yes, well, but this chi no alpha depends on the P no alpha, which is the pressure at which I brought the plasma by compression alone. And I don't know what that is, right? I mean, I can't measure it. So I don't know what that is, the pressure that the plasma reached just by compression without alpha particles. So I don't know what it is. So I cannot know what chi no alpha is. I cannot measure it, okay? So if I cannot measure it, then I cannot tell what is the yield amplification due to the alpha particles. Okay, so I can do one more thing here. Let's see if there is a way to measure the no alpha Lawson parameter, that chi no alpha. So I go back and estimate the confinement time. So what is the confinement time of a plasma that makes fusion reactions because of the high temperatures, but is surrounded by a dense shell whose inertia is confining this hard plasma? So, well, the confinement time is dictated by the inertia of this shell. So there is a high pressure here, but this pressure is only going to last until the shell is around it. And of course, this pressure tries to displace the shell and push it out. So the shell motion is just governed by the Newton's law. The mass of the shell times the acceleration is equal to minus 4 pi the pressure times the surface. Sorry, pressure times the surface, right? That's very simple. Okay, and then I can estimate the confinement time by replacing r double dot, which is the acceleration, with r over tau squared. And now I get tau as the square root of the mass of the shell, the pressure, and the radius. Okay? Now the mass of the shell, if this is a thin shell of thickness delta, well, the mass of the shell would just be the density of the shell times the volume, and the volume is just the thickness times the surface, and the surface is just r squared. Obviously, the volume of this plasma, if it is a thin shell, I can neglect delta with respect to r, it's just r cubed. Okay? So now I derived an estimate for tau, okay? And I know that the shell mass can be written in terms of shell density and in terms of thickness of the shell. This quantity here, density times thickness, okay, is called the areal density. Okay, and then I know that the volume trivially is r cubed. So now you have all these relations. What I'm going to do now, I'm going to take these relations, okay, and substitute it back into the yield formula. So the yield formula, the number of fusion reactions, is the pressure square, the confinement time, and the volume. I found the confinement time, I found the volume before. I substitute it back in there. I know that the Lawson parameter is p tau divided by a constant. Okay, I rearrange the parameters, and I get this relation. The Lawson parameter, p tau, basically, cube, goes like the yield, the shell mass, and the areal density. Now, I know what is the shell mass because I know what is the original mass of the shell, okay, because when they make the shell, they put a given amount of deuterium and tritium. So I know what that shell mass is. The areal density is something that I can measure, okay, and if you're interested in how to measure areal density, I have a slide at the very end. So this is actually I can measure it, okay. I can measure the yield, then I can measure the chi, right? However, the yield that I measure is only the yield that is produced in a real implosion, because that's what my measurements are, where the alpha particles are on in a real implosion. So this would be the yield with alpha particles. The difference of chi with alpha particles or without alpha particles is just that the yield is with alphas or is without alphas. If somehow, for magic reason, you can generate an implosion where the alpha particles do not heat up the plasma, then the yield will be the yield without alphas, and you will get the chi without alphas. If in a real implosion, however, the yield has alpha particles changing the yield, and so the yield will be with alphas, and you will measure the chi with alphas. However, you can see the ratio of chi alpha and chi no alpha is just the ratio of the yield with alpha or no alpha. So there is a very simple relation between the chi that I can measure, chi with alphas because the yield that I measure has alpha in it, and the chi no alpha, okay, that I cannot directly measure, but they are related by this, okay, times these two yields. Now, the yield no alpha I cannot measure. I can measure the yield with alphas. Okay, but this is the last step. So I just showed you before, the amplification of the yield with alpha with respect to no alpha only depends on the Lawson parameter without alpha. But the Lawson parameter without alpha I just derived for you depends, and the Lawson parameter with alpha, they are related by a very simple relation, which is the same ratio of the yields. So therefore, if there is a unique curve between this ratio and chi no alpha, because these two are related by the same ratio, then there is a unique curve between the ratio of the yield and chi alpha. Okay? Okay, so what do I do in the experiments? So in the experiments, I can measure this chi alpha, because the yield with alpha, that's one of what I measure in the experiments. I know what is the mass of the dt, and I can measure the areal density. So I measure this parameter chi alpha. I go up here, I get the yield amplification, okay? And then if I want, I can also extract the Lawson parameter without alpha. Why do I really want to extract the Lawson parameter without alphas? Is that because that tells me where I am in terms of how far I am from ignition. Because we just show you that at the chi no alpha equal 1 is the ignition condition. So if I get, let's say, 0.75 from this measurement, means I'm only 25% far from ignition in terms of pressure that I need to achieve. Okay? So let me go to the actual real results. Okay? So this is NIF shot 140120. Produced the highest yield to date. They measured the yield. It's 10 to the 16 neutrons, roughly, 26 kilojoules of fusion energy. They measured the areal density, roughly 0.8 gram per centimeter squared. The mass of the DT is known, is 0.17 milligrams. The temperature is also measurable, it's 5.6 keV. And the radius of the half plasma, you can actually see the half plasma, is 33 microns, okay? So first, I did a very simple estimate. I have a formula I derived some time ago of how much yield you can expect from a given areal density, a given mass, and a given temperature. So I plug into the formula that is right here, and I find that the yield that you can expect from the simple analytic formula is 1.4 10 to the 16 neutrons. They measure 10 to the 16 neutrons. So their yield is consistent with our understanding, a very simple understanding of the implosion, okay? So they get a yield that is consistent with what one would predict using very simple physics. They do complicated 2D simulations using the Hydra code, and they get 1.6 10 to the 16th. What they measure is 10 to the 16th. So it's close, okay? So the actual yield over clean, which is the yield measured divided by the yield predicted, is basically 70%. So that's a very good shot. You know, there is nothing anomalous about this shot. It basically follows what we knew about implosion physics. So what about in terms of yield amplification due to the alphas? Well, this is the actual chi alpha that you can measure. You can measure the areal density. This is the full formula in gram per centimeter square. They can measure the number of neutrons produced, and we know the mass of the T is 0.17 milligrams. This is 10 to the 16 neutrons. You substitute there, and you get a chi alpha of 0.94. You go back into that curve. Now here in this curve, this is the simple model that I showed you before, and this is corroborated by simulations. Those are simulations in 1D. Those are simulations in 2D. They all follow these curves, more or less. So now I have measured the chi. I go back here, and I estimate the amplification of the yield, okay, due to the alpha particles. And the amplification is roughly 2.5, 3. So the alpha particles almost tripled, the number of fusion reactions. So that's real fusion plasma, where the alpha particles increase the number of fusion reactions by more than a factor of 2. Now you can also estimate how far you are from ignition, okay, by going to the other curve that I had before and estimate kino alpha. You find that's 0.65. So you need kino alpha 1 to ignite it. So they are basically at 65% of the p tau, the Lawson parameter required for ignition. They need another 35%. Okay, so I'm going to skip for a second. There is another way to measure this, okay, and I'm going to skip this. But anyway, you get the same results, so that's the important thing. So how was this obtained using by the Livermore team? And Omar Hurricane was the PI on these experiments, and that was in the Nature paper. So they started the initial campaign getting very low yields. So those are all the yields that we're getting for basically the first 3 years. And then all of a sudden, in the last less than a year ago, okay, they started getting much higher yields. And this is the slide that Hurricane showed at the APS DPP meeting in November. And since then, there are other shots, it's even much better performance than that. And I added those shots. So they got a lot more number of fusion reactions went up considerably since then. So what they did, basically, in order to go from bad implosions to good implosions, they just changed the laser pulse, okay? So this was the so-called low-foot laser pulse. So that's what they've been used on NIF for the first 3 years, okay? So in black has, so you have a little blip here that's called a picket, launches a weak shock into the target. Then there is another compression here, and then there is another shock coming from here. And because you're sending, so here the shock is weak, you are also compressing gently, and because you are pre-compressing before launching a shock, then when you launch a shock through something that is higher density, then you lower the entropy. So what happens is that this shock, this pulse shape, because it has a low entropy shock, so remember, the stronger the shock, the higher the entropy. So this is a weak shock, so low entropy. Pre-compression and the shock, that's low entropy. So this was a low entropy shock. So what is a low entropy, low entropy shock? Low entropy means that the target is driven on low entropy. And when the target is driven on low entropy means that when it stagnates, because the entropy is low, the density is going to be very high. And that's what you want to ignite. You want a very high density, high good confinement shell around your hotspot. So you want very, very high densities. However, as I can show you in a minute, these low entropy shots are unstable to hydrodynamic instabilities. So what the Livermore folks think is that, yes, the codes were telling us that, the shots were going to perform well, but it seems like hydrodynamic instabilities are worse than they thought, and so the shots perform poorly. So they took a step back, and they used a so-called high-foot shot, where the picket here is stronger. Okay, you can see here. So it launches a stronger shock, so higher entropy. They removed this compression, and therefore they are shocking now a lower density. So what that means, it means that they are raising the entropy of the capsule. So now, with this higher entropy capsule, okay, they got much better results. So at higher entropy, as the shell implodes, it's going to be lower density, so it's going to be thicker. And so if you have hydrodynamic instability, it can be better tolerated by the capsule because it's just thicker. The entropy of the capsule is usually referred as the adiabat, as alpha. This alpha here now has nothing to do with alpha particles. That's the way people in ICF call the entropy. They call it alpha. Okay, so a shell driven on a higher asymptote has a larger thickness and lower inflight asper ratio. So the thickness is trivial. The thickness of an imploding shell is just the mass over the density and the surface, right? So R squared. Now, if you apply the same pressure, and that's what the X-ray driver does, then the density is just the pressure over the isentrope, the alpha, to the 3/5, okay? So therefore, when you substitute this back in there, you get that the thickness of the capsule in flight goes like this entropy to the 3/5. So the higher the entropy, the thicker is your in-flight thickness, the larger is your in-flight thickness of the shell, okay? You can calculate the in-flight asper ratio, which is the radius over the thickness. I just substituted the thickness back in there. That's all I've done. Okay? And then I multiplied, divided by the velocity of the capsule squared. And so now here I have the mass times the velocity squared. That's the kinetic energy. On the numerator, I have the applied pressure times the volume, R cubed, and that's the work. But the work done by the applied pressure is basically the kinetic energy, so those two cancel. And we end up with the in-flight asper ratio, which is that's the velocity of the implosion square over the entropy to the 3/5 divided by the applied pressure. Assuming that the applied pressure is the same for all the shots, then this in-flight asper ratio depends on the implosion velocity and depends on the entropy. The higher the entropy, the lower is the in-flight asper ratio. So why this parameter here is so crucial, the in-flight asper ratio, and why I want to keep it low, okay? So it's because of hydrodynamic instability. So imagine you have two fluids. One is a dense fluid, and one is a light fluid in a gravitational field. Then the interface between the two is unstable to the Rayleigh-Taylor instability. You have all kinds of bubbles that forms a spike, and these bubbles here, which is the mixing front, penetrates into the dense fuel. The penetration with H is a function of time. Okay, so the penetration H of these bubbles into the dense fluid goes like the acceleration times t squared times a constant. Okay, but now gt squared, okay, if this lab is accelerating, okay, is just 1/2 gt squared is the distance traveled by an object accelerated with acceleration g. So gt squared is just twice the distance traveled. If you think you are accelerating this capsule over a radius that is half the initial radius, then you substitute into d half the initial radius, and you get that the penetration of the Rayleigh-Taylor front into the dense shell goes like a constant times the radius. This constant is a small number. It's calculated numerically by many simulations. It's roughly 0.05. So the critical parameter now depends on this. This is the penetration of the instability fronts into the shell as it implodes. If this penetration becomes larger than the thickness of the shell, it means that the shell is completely penetrated, it's broken apart, okay? So the critical parameter is the ratio of the penetration of the bubble of the Rayleigh-Taylor instability, okay, divided by the thickness. So I substitute H, which is beta times the radius, but radius over thickness is the in-flight asper ratio, okay? Beta is 0.05, so if the in-flight asper ratio is larger than 20, this number is larger than 1. It means that the bubbles of the Rayleigh-Taylor instability have penetrated all the way through the capsule, and the capsule is broken up into pieces. Okay, that's what it means. So keeping the in-flight asper ratio low is key to suppress the hydrodynamic instabilities for completely penetrating through and breaking up your capsule as it implodes. Okay? So this is well known. I mean, there's no mystery here that somebody had a fantastic idea. I mean, this is what you learn in my course, if you ever want to take it, in the first week. Okay, so it's basic, very simple stuff. So if you have a high IFAR targets where H becomes larger than the thickness, then you end up with a broken up capsule that breaks up into filaments like this, and then you have a piston that is broken up and can't compress anything. Okay. This is just the growth rates. Same thing, if you calculate linear growth rates, so you find that the capsule with the high foot is much more stable than the low foot. But this is basically the key simulation results. So this is from Livermore. This was their original capsule, the so-called low foot. That's low entropy, that is more unstable. You can see that the growth is higher than the high foot. These are two different high foot designs. You can see that the growth with respect to the thickness is a lot smaller here, is a lot better here. It's much smaller growth with respect to the thickness. So this capsule can survive the implosion. This is a peak compression. Okay, you can see here a much larger growth, a peak compression for this capsule than this capsule and then this capsule. So the high foot is much more stable than the low foot. Okay, to be expected. No surprise there. Okay, so assuming that this is it, this is basically almost one last slide, or I have another one. So despite these exciting results of the so-called high foot campaign, so the path to ignition is uncertain, okay, with current indirect drive targets. So this parameter was the Lawson parameter has to be 1 for ignition. You can rewrite it in terms of kinetic energy of the implosions. This is the yield over clean, which is a measure of the uniformity of the implosion. So this is the ratio of the yield that you get divided by the predicted 1D yield. The applied pressure, okay, that's the ablation pressure from the X-rays, and the inflight asper ratio. So if you want to get ignition, now chi, remember, is 0.65 in the best experiments I've done. You need to get chi to 1. What can you do? You can act on each of these parameters. So you can act on the kinetic energy, but if you want to just act on the kinetic energy, you will need to get the kinetic energy up by a factor of 3 to make up the distance left and get chi equal 1. So there is no way we can get 3 times more kinetic energy from these implosions, okay? So the yield over clean, which is a measure on the uniformity, is already at 70%. So, you know, at the most you get 100% of the yield, the perfect 1D implosion. Okay, so at the most the Yokke can go up a little bit. It's never going to go up by 2.5 to bring this to 1, just because the maximum value of the Yokke is 1. The ablation pressure, well, the applied pressure, you know, if you want to bring this to 1, it has to go up by a factor of 2. I can't think. I mean, you can't really change much the ablation pressure. You will need twice the power on NIF, and we are already at 500 terawatts, right? 400 terawatts. So the only way is to increase the inflight asper ratio by roughly 50%. Okay, so that means that the shell, as it implodes, has to be thinner by 35%. So that whether, you know, other instabilities will allow us to do that, it's a question. It's not obvious. Maybe this is really too much to ask to increase the inflight asper ratio, you know, and hoping that the hydrodynamic instability is not going to destroy the implosion. So this is what they're doing now a little more. Okay, that's their strategy. This is my last slide. So that's the current path that they have. So they had to increase this chi to 1, and the inflight asper ratio depends on this one. They can't do much about it. Maybe they can do a little bit. But basically, they have to increase the implosion velocity or lower the adiabat, or the entropy. So they are gradually increasing the IFR of current targets. That's what they're doing. They are going to be increasing the velocity. They are making the target thinner at the beginning, so they have less mass, and they are driving it to the higher implosion velocity, you know, risking hydrodynamic instabilities. And so they are doing thinner shells. They are also lowering the isentrope by basically going slowly back towards the low foot design with the weaker shocks that set the shell on a lower adiabat, a lower isentrope, and I'm going to lower the alpha to increase the inflight asper ratio. So that's what they're doing. The other thing that they're doing is say, well, this is the current targets. It's a plastic ablator. They are also looking into changing the ablators. Going to be using a high-density carbon, which is diamond, okay, and beryllium. Those are the two ablators. The high-density carbon is supposed to be more stable to the Rayleigh-Taylor instability because there's a gentler profiles of density. So the so-called density gradient stabilization, for those of you that study Rayleigh-Taylor, it's the same thing anyway. In all kinds of instability, you have density gradient stabilizations. So that's going to be better. There also another advantage of diamond is that because it's denser, and then the shocks travel faster for the same mass, and therefore they are going to have shorter pulses, and they can eliminate therefore the gas inside the hole round, and they can use vacuum hole rounds, which will help them recovering some of the driver energy that is lost by laser plasma instability driven by the plasma inside the hole round. And then the other possibility is using beryllium targets, which have greater hydro efficiency. So they couple the energy better. And therefore, they can use a thicker target because they have more energy now, effectively. And more thicker target will be more stable to the Rayleigh Taylor. So those are options. This is another option. So there is a parameter space that can be explored. Whether that is enough to make K equal 1, it's not obvious. So that's to be seen. So, conclusions. The recent results from the NIF are exciting and give us hope for achieving burning plasma conditions. For the first time in the history of controlled fusion, a DT plasma has produced more fusion energy than the total energy supplied to the plasma itself. So the shot that I mentioned to you produces 26 kilojoules of fusion energy. The DT received only 10 kilojoules of fusion energy. It's a nice result, nothing to make a huge deal out of, but it's a nice result. Actually, I think what is a very nice result, and I think this is much more significant, is that for the first time, the alpha particles have increased significantly the number of fusion reactions. They have more than doubled the number of fusion reactions. I think this is a much more important result than this one of the energy bands. So this is only fusion physics, and reaching any conclusions about fusion energy is premature, as I mentioned to you. The possibility of producing a burning plasma is real, and the indirect drive approach seems getting close to it. So the path to ignition and gain is still uncertain. Okay, whether we're going to get ignition anytime soon, it's not gain, it's also uncertain. But obviously the prospects are a lot better than they were 12 months ago. Thank you.
Okay, thank you, Ricardo. We have time for a couple of questions anyway. Yeah.
What was learned from the experiments that they hadn't known from simulations?
Well, the initial targets that they used in the campaign, when simulated, they were not showing that they were going to break up due to the Rayleigh Taylor instability. So the simulation was showing that this target would ignite. Okay? So if you believe, as it looks like, that the Rayleigh Taylor instability, the hydrodynamic instability are the cause that prevented achieving ignition, then obviously the codes are under-predicting the effect of hydrodynamic instabilities. That could come in two ways. One way is that the codes under-predict the growth of those instabilities, or the codes are right and we are not inputting into the code the correct seeds of the instabilities. Okay? So either ways is possible. So, but right now, the consensus is that it's hydrodynamic instabilities that cause the failure of the initial targets that we're shooting. Yes?
Yeah, in the back.
So with regards to national security, I'm curious if the United States has other means of testing nuclear armaments.
Well, I don't even have Q clearance, so I'm not even sure what to tell you, okay? I hope they do, I don't know. For the safety of the stockpile, I hope they know what they're doing.
Any other questions? If not, let's thank Ricardo again.